All right. A couple people were smart and stayed home today. So the lecture videos are posted. I don't know if you guys want to at least go on there and check them out. I don't have Canvas pulled up right now, but there's a link at the very top under the week 0 module. It just says lecture videos. You click on that, and then that's where the bucket should go every day to say, hey, I wanted to see the September, whatever, 14th lecture. So click on that one. You can watch the show. So give you an idea if you haven't seen, there's going to be capturing the document camera, capturing whatever the other slideshow is, and then a little video kind of generically following me around. So kind of get the whole feel for everything if you don't make it to this today. So that's announcement number 1. Announcement number 2, quiz 1 is due tonight. So, yeah, it's Tuesday. So make sure you get in there. I drop your lowest quiz of the year, and this is the easiest one, so you don't want this one to be your drop. So don't forget, put yourself a little reminder in your calendar to Tuesday nights to do the quizzes. Remember, you get 2 attempts, 30 minutes per, with as long of a gap as you want in between. So think about doing this with a little bit of time before midnight so that you can think if you mess things up. Okay? Last thing about quizzes, they're all numerical. Well, most of them are numerical and the numbers change. So work your problems out algebraically, because if you have to take a second attempt, your number 1 isn't going to be 3.2 anymore. It's going to be a whole new number. So you want to be able to plug in the new inputs and get a new output rather quickly. And solving algebraically is the best way to do that. Discussion starts tomorrow on Canvas under the week 2 module. If you kind of scroll to the bottom of the week 2 thing, you'll see discussion problems. You might want to download those or take a peek at them so that you can follow along more easily in discussion, maybe even print them off. There'll be 2 or 3 problems a day that your TAs will try to crank through. So it's nice if you got the problem in front of you so you can follow along more easily. And then after Friday's discussion, we'll post the solution. So if you couldn't make it for whatever reason, now you got access to what we did. But remember, discussion attendance is mandatory, so when you show up, there will likely be a sign-up sheet. So bust out your pencil, initial, and so you get credit for being there. And last thing, office hours. We're running office hours already this week. One of you guys came yesterday. I've got mine today from 3 to 4. They're on Zoom. The Zoom link is also in Canvas. So if you want to ask us some questions, Canvas has a list of our office hours times every day of the week. And then that Zoom link, jump in there and come talk to us, okay? Generic questions, layout of class, how things are going. All right, let's get rolling. So, before we push on, we have a little bit of something to finish up from last time. So last time, we didn't really do a whole lot. I'm going to, last time we talked about position. And we used R as our vector. All my notes from today and on, I think, use S. So, tricked you. We're going to swap back and forth between these. So we've got position. We talked about velocity. V is the time rate of change of position. And then briefly at the end, we talked about acceleration. That's the time rate of change of velocity, or the second derivative of position. So we want to hit on that one a little bit more today before we move on to the new stuff. We had a wiggly path moving from the left side to the right side. Last time we got together, we said, hey, as I look at my changing in position as a function of time, my velocity, and the closer and closer and closer I got to making a small change in time, we could see that our velocity was tangent to the line. So wherever this curve is, maybe it's here this time. V of t. Pick any point you want. Just draw a tangent line to it. Acceleration, not so much. Acceleration is going to have two pieces. I think I briefly described them last time as being in my minivan, and you had an acceleration that you could feel from speeding up or slowing down. So slam on the gas, boom. You feel that acceleration in the direction you're going. Hit the brakes, you feel that acceleration or deceleration in the direction you're going. So that part is the tangential. So acceleration, two parts. There's a tangent part, and this is speeding up or slowing down.
So the economics part is just kind of like a set of tools that can help us narrow down alternatives or analyze what they might be.
Pretty easy to understand, right? Hey, I'm going faster, I'm going slower. This is also going to be tangent. So in the direction you're going, maybe I'm going this way, and I'm speeding up. So if I just draw that above. This is my acceleration in the tangent direction. We're going a little faster at this point. Maybe when I'm going up the hill, I'm slowing down.
So there's a couple different types of ethics.
That's my tangential component of acceleration at that point.
Something that comes up in a lot of engineering classes.
Acceleration pointing backwards doesn't mean I'm going backwards. Acceleration pointing in the opposite directions means we're slowing down,
But it is
right?
pretty important.
Okay.
Kind of like medical professions where
And then there's a normal component.
you follow a particular code of ethics.
And this is changing direction.
World, right? We have some things like universal morals or universal ethics. These are fundamental.
So acceleration, the time derivative of velocity. So we got to account for velocity's change in magnitude, speeding up or slowing down. But also, we're changing the direction of our velocity vector. This is stuff we're going to talk about more when we get to curvilinear coordinate systems, but it's just kind of nice to introduce it in the beginning of class. So I've drawn out my velocity vector here. Tangent as best I could. And then what if I moved a little time down? Just a little ways over here. I try to draw another velocity vector.
Personal morals or ethics are talking about beliefs that you, as
They're roughly the same length, as good of a drawing as I can do. So if they're roughly the same length, that means we're not slowing down or speeding up. But their direction is much different. So this is v of t plus
there's this idea that steel
delta t.
right? You may have more complicated thoughts about what that actually means and what constitutes
So our acceleration is our derivative of velocity.
engineering is the bottom part,
Or, we can think of this as
or in our case,
the limit as delta t
a lot of professions
goes to 0
standard or code of ethics.
of v of t
That's meant to guide how you work
plus delta t
with them and how you
minus v of t over
so just
some change in time.
with personal morals
So the acceleration is as we squeeze this guy down.
come up for engineering,
But I write this just
and that could be accomplished
to help us visualize what's going on.
ethics and what you are
The numerator here, let's get these as vectors.
professional ethics.
I care about their direction.
They can
So
come up at any stage.
I've got my velocity at some additional time,
You may feel pressure
and then minus my velocity at the initial time. So that we can do here with our little vector picture.
factors. Make sure
So this guy here, this first piece,
someone else may seem like a really
is that vector.
good time.
This guy, or v of t,
Maybe you
is this vector right here.
have your personal connection,
So if I'm subtracting them, you can kind of think of them as adding
or you have some
the opposite of this one.
side
So I'm going to try to redraw
to be on
this vector, but I'm going to subtract them. So I'm going to stick that one
things
on here, but going in the opposite direction.
in their operating system.
So this would be like minus v of t. So this top, when I do this vector subtraction, I get something
So for engineers, the National
Points
Society of Professional Engineers has a code
towards the center of curvature.
for engineers, but then
So this is my
professional societies, like if you're in American Society
AN.
of Civil Engineers,
Now, I don't know its magnitude,
codes,
but I know its direction.
this,
The normal component of acceleration is always going to point towards the center of curvature. So here,
be out there and
we're cruising around the curve. Center of curvature goes this way. I know my normal direction is pointing in. Over here, it's a little hard to show, but maybe let's just pretend that this is perfectly straight here.
what are some
if this is perfectly straight, it has no curvature, there is no normal acceleration at this point. There's only a tangential acceleration. So maybe here we'll say normal acceleration is 0 because it's going in a straight line at this point. But our magnitude of the normal acceleration is depending on a couple of things. I've got my velocity, so we've got this idea of what direction it's going, but we're changing direction. But how large our normal acceleration is, its magnitude, depends on how fast we're going. So it depends on velocity and the curvature. So our intuition should kind of match this. You think, if you're driving your car at 70 miles an hour and you're on the highway and there's a nice, smooth, swooping turn. You're going 70, the curve is smooth, you don't feel much acceleration kind of like trying to throw you out of the car. But if I was doing that same curve at 200 miles an hour, this is a little sketchy, right? You think that maybe you're going to slide off the road or do something dangerous. That acceleration in the normal direction would be increasing. Or you're going 70 miles an hour on a nice highway, nice and smooth, or you're going 70 miles an hour on a windy Wisconsin country back road. These curves are really tight, right? Well, what you've done is you've shrunk this radius of curvature, so your accelerations go way up. So we'll hit this stuff a lot more next week, but it's kind of interesting to see acceleration, not just a scalar value. It's a vector, so I care about it's changing in speed, speeding up, slowing down. I also care about changing that direction of my velocity vector. So two different parts going on. Again, we'll talk about that more in a little bit. That was really the last thing I wanted to tell you from day one. And this is just a map of that. Okay. So on to the new stuff. So today we're going to be talking about one-dimensional motion. So super exciting. You think all we're going to be doing is moving in the path. So if I can tell you exactly where we are, if I just define our position. Hey, I moved out to here. I moved out to here. 1D. We're going to look at this, and we're going to look at circular motion. But maybe even just chat about it for a second. So here I might have different positions, S1, S2, S3. If I tell you that S3 distance, you know exactly where we are. We're sitting on this dot. For circular motion, we're going to assume that this radius is constant. So constant radius. And instead of giving you a position S1, S2, S3, I can give you an angle measured from the x-axis positive counterclockwise. Give you an angle theta. So if I tell you your angle is 67 degrees, that'll put us at this point. Angle is 180 degrees. That'll put us all the way over here. All I need to tell you is the angle that we're sitting at, and you know where we are because we're stuck on this circular racetrack. So 1D motion today. We've kind of set the stage for acceleration and velocity and position. But today we're going to add a few wrinkles, a little bit of math to make things a little trickier. So last time we got together, day one, we talked about position. And we gave position as a function of time. Hey, find the velocity. Velocity, as a function of time, was the time derivative of position. Acceleration, time derivative of velocity. or the second derivative of position.
We have interest paid.
So if you needed to jump between
Paid interest when
position to velocity to acceleration, if I'm working my way down this chart, if I have whatever complicated, maybe it's a polynomial of position as a function of time,
so if you took out
I could just take derivatives to get to acceleration. If I gave you acceleration as a function of time, and we're trying to figure out position, you're going to need a little bit more information.
a personal loan,
You're going to need to know some initial conditions.
dollars, but what you pay back
You might need to know, hey, what is my
rate will depend on a lot of different things, like where you borrowed
velocity at time 0? Or some other time, some initial velocity. What is my position
and we earn interest
at time 0?
person or
So in order to be able to integrate, if you're given a function of acceleration as a function of time, to get those constants of integration, you need to have some more information.
so if you had a savings account,
That's where initial conditions jump in.
you, let's say 2% per month,
So our basic definition of acceleration,
$3,000 in it when you started college,
dv dt.
you would have a larger amount
Everything we're going to do kind of builds off of this. Acceleration is the time derivative of velocity. So the wrinkle we're going to throw at you today, well,
let's say we bought
what happens when I give you acceleration that's not a function
pay
of time?
10,700.
What if I give you acceleration
Something we could figure out from that is the actual
as a function of velocity?
that we paid
Well, you certainly can't just integrate it with respect to time, right? It's going to throw some difficulties at you. Acceleration as a function of velocity,
So how much did we actually pay back?
it's a
$10,700
fluids problem.
minus the principal.
Think about acceleration. We talked about Newton's second law. Force is equal to mass times acceleration.
And that's
So acceleration, if it's a function of velocity, or that force being a function of velocity,
1 year divided by our
well,
principal of
that's
$10,000.
anytime you put your hand out a car window.
7%
You're cruising around city streets going 20 miles an hour, just feel a gentle breeze. But you stuck your hand out the car window on the highway, 100 miles an hour, you're going to feel a force on your arm. Pretty heavy, right? So that's just viscous drag from your arm being in a fluid as it's moving at some velocity. Maybe it's magnified when you think of being underwater and you're just kind of gracefully floating, pulling, not much force on your arms. But if you're like Michael Phelps swimming as fast as you can, you're pulling really hard. So when you see fluids problems, acceleration as a function of velocity. The other one that we're going to deal with today,
30%, but it depends.
acceleration as a function of position. And this, you see a lot of times with springs.
A lot of people buy houses in 20
You know, I got a little spring here.
the interest rates on mortgages was really low. Under
Maybe I stretch this spring to this new position. It's a little bit longer.
people sold their old house and bought a new house.
As I pull it a little bit, that takes a little bit of force. As I pull it 2 little bits, that takes 2 little bits of force. So the force you see, and then
Okay? You get the money
subsequently the acceleration you see, is going to be a function of position. How far you pulled that spring, it's going to have more force, more acceleration. So we're not always so lucky to get
personal loans or credit cards.
acceleration as a function of time.
Interest rate you're offered
Sorry.
depend on things like your debt to income,
But what we'll do today
credit score,
is these next 10 slides are roadmap. When you read a problem and it says, oh, I've got acceleration as a function of velocity, I've got acceleration as a function of position, I need to figure out position, I need to figure out velocity. How do we go about getting there? And that's what today's talk is. So the first one,
an example.
acceleration as a function of time. So if you're checking out these notes, and you're saying, let's see if this thing works. Oh, it does.
But if you took out a loan
You're trying to follow our roadmap here. Look what, I'm given acceleration as a function of time. A as a function of t. I want to figure out velocity.
took out a loan of $10,000,
Hey, A
you only have to repay $8,000. So imagine if you
got acceleration as a function of time. My definition of acceleration, dv dt. I'm going to separate variables to get t on the same side as acceleration because that's a function of time.
yeah, that's
So I'm going to have
I can't off the top of my
a of t. I've just scooted this guy over.
real
dt
life negative interest rate, which is pretty
is equal to my velocity.
across one so far, but I'm sure they're out there.
So now that we have this,
So another
we can integrate both sides.
again, we talk about earning a return on an investment.
What are your limits of integration?
Rate of return is a concept.
Hey, I'm integrating acceleration with respect to time. I better have time limits. T0 to t.
You might find
On the other side, I'm integrating velocity.
the same.
V0
Just a different
to v.
But that perspective
So the right-hand side becomes v minus
really, really important.
v0.
When we get to cash flow diagrams,
The left-hand side, I really can't do anything with.
how that could really mess up your analysis. So it's important to consider who's being paid and who is paying and when are those things happening. So again, if we're borrowing,
Go ahead and solve this for v.
perspective of interest,
That's what's boxed in this note.
but if we are the lender or the investor, then
Okay?
we call rate of return.
Not too complicated.
We want to know
Those are the ones that I think
depending on
our brains process pretty easily.
a project or business or whatever it
You want to take this one step further.
might be, right?
Now you've got velocity.
The
Oh,
amount
I'm going to do this. I'm going to sneak a t in there.
1 year ago
Velocity as a function of time.
right now,
And you want to get to position.
10% per year.
So for position,
We want to know the amount of interest then that was earned during
I've got velocity as a function of time.
that total
And I know that my velocity
is $1,000. That's the sum of whatever our original deposit was.
is the time rate of change of position. So just like acceleration was a time rate of change of velocity, velocity
So we have that total
is our position changing as a function of time.
whatever our deposit was plus
Well, same trick.
times some interest rate.
Scoot this dt over.
Let's call the original deposit X.
I've got v
That can help
dt
simplify that equation.
is equal to
When you write it out like
ds.
that, you see that we only have
Let's
one unknown,
integrate both sides.
right? We can equate that
Look at your limits of integration.
that total amount
Look at your integrating variables. So I'm integrating
to our relation,
the right-hand side with respect to s,
simplify it a bit,
s0 to s, and the left-hand side, that's with a t,
and then we can solve.
t0 to t.
And when we do that, we find that that original deposit that
This is going to give us
was $952.30,
our position as a function of time,
which means that we earned
which is what's on this box here.
an amount of $47
Laziness prevents me from rewriting it.
difference
Um,
between our original
the one gotcha I will throw out there,
and amount.
which is
That's a
maybe a little
simple example of
rough on the notes here.
something like
If I look at
a problem.
what we're getting, so velocity is going to be the integral of acceleration. So to get to position, I'm going to have to integrate acceleration twice.
Have them on canvas,
So we see a double integral
section 5.
down here.
Where I have some
And we're integrating acceleration from t0 to t. The one thing we can't do is when I go to integrate acceleration, I can't really substitute in these definite integrals right away.
definitions. I have some equations.
Because if I do that, I think like maybe I'm giving it some acceleration with respect to time is, say, 2t. I don't know. Easiest thing I could think of.
The factor tables for
So if I integrate this, and maybe I'm going from
glossary. So if you're ever looking at a term, you can kind of look through the things there.
0 to 2,
So there's a couple of things that
my acceleration here,
and we'll learn
2t, integral of 2t,
kind of a base set that will come up all the time.
that's just t squared.
We usually use
Evaluated at 0 and t and 2. If I plug in and I evaluate this integral right away, I'm going to get just a number. Looks like I'm going to get the number 4. And then I would come back here with my number 4, and I would integrate 4 with respect to time, and I just get 4t.
amount of money in future time.
No, I want to bring along this as an indefinite integral when I'm integrating, so I can integrate it twice, and then once I do that second integral, that's when I want to imply my end condition. So instead of having this as an indefinite or a definite integral, leave this guy as an indefinite integral, and if you have to solve for that constant with your initial conditions, you can do that. And then when you integrate it for velocity, or integrate to get to position, you're still going to be integrating with respect to t. And you're not losing that, that time dependence. So we don't want to get rid of the time dependence too early by creating that nested integral as a definite integral.
That's what we're talking
Bring it along and then swap out.
about. Symbols come up.
I think that's a quiz for next week.
And for that symbol A, it always represents a uniform amount, meaning the same amount each period. So if that's pay, we're talking about a payment, an annual payment, the same amount every year. If there's situations where it's not the same amount
Okay,
every year,
those are the boring ones.
have to deal with those.
Is that on the quiz for this week?
And we have cash
There he goes, the quiz for this week. Shh, don't tell anybody.
cash coming in. We usually use a plus sign to represent cash inflows. That can be revenue, receipts, income, savings.
Yeah, I guess in my mind that still counts as, you know, what we did.
Of cash outflows, we generally use a minus sign.
Yeah, but it's, I guess, this stuff, right? That's still day one.
Disbursement,
Acceleration is a function of velocity, or acceleration is a function of time. So,
money going away. And a lot of time our goal
okay.
is to look at, based on those
So,
inflows and outflows,
now the interesting ones.
the net cash flow.
Acceleration as a function
That could be
of velocity. This is our viscous drag problem.
your project life. You're looking at all your inflows and all your outflows to figure out what's the net cash flow in that.
So what do we do here?
And this
I've
is
got acceleration
really nice when we use Excel.
as a function of velocity,
Populate cash flows into a table
dv dt.
and have it do some nice
So again, kind of how we solved the acceleration as a function of time. We did separation of variables where I moved the time over and then I integrated.
of a given
If I move the time over, now that's playing with a
assume that whatever's happened
velocity variable.
at the end of the period.
So I would need to
Otherwise,
move that guy to the other side as well. So I'm going to move time to one side, then I'll move this other term to the other side. So if I rearrange this equation,
$500 at the end of the year,
dt is equal to dv divided by
idea is that we just assume that, let's say,
acceleration as a function of velocity.
$600 in
So
for 2 years.
acceleration
We're going to assume that that
as a function of velocity, maybe you get 14v squared minus 7. I don't know.
when we look at ours,
Just some function of velocity. I have a velocity dependence on my acceleration term. That's all we're saying with that.
might look like. We want to show the cash
So now we can go ahead,
arrows to approximate scale.
integrate both sides.
It's not, you're not
My time side, t0 to t. My velocity side,
there and measure your arrows.
v0 to v.
Engineering paper, sometimes
And I'm left with
Excel, or
t minus t0 is equal to
if you can try to keep them
the integral
helpful to you to see what's
of
going on.
dv over acceleration.
Time period, right? We have a time period here.
So this is
Period 0, present time, and period
not always going to be fun to do.
2, and that could again be
And my warning will be
a month.
today's homework and today's lecture is probably the hardest math we're going to see all semester. So if you can remember a few integration tricks from calculus, and you can get through today, the rest of it, I hope, is going to be a breeze. I'll only ever ask you to integrate and differentiate easy things. Things that I can remember 20 years after calculus. Polynomials, cosine sines, things like that. But today, we might not be so lucky. So today things are going to be a little trickier. So one thing to help us solve something that looks like this,
When you draw them, if you want to do it opposite, okay, that makes more sense to you.
remember that ln of x is equal to the integral
Make sure you know which one is cash outflow and which one is cash.
of dx over x.
I like
One of those nice things to have in our back pocket.
that dollar amounts on
You guys probably have fancy algebraic calculators that can integrate this for us, but
this was a $100 payment.
we'll go old school today.
Payment, money going in.
So we'll do a problem that actually uses this later, but again, nice thing to have in our back pocket. So
It's not going to be,
what does this give me? This gives me, if I solve this out, my time
we're going to draw them a lot in
as a function of velocity.
we're looking at where things are occurring. And that becomes really important when we talk about
Maybe if I wanted to figure out velocity,
shifted theory.
I would have to invert that equation. So
So
let's pretend that I've got
actual numbers.
t is equal to
Let's say we have a
7v
chemical engineer who wants to
plus 4.
deposit some amount
Totally unrelated. Let's pretend like that didn't exist, okay?
so that she can withdraw
This is time as a function of velocity. If I wanted to solve this for velocity, t minus 4 divided by 7. Now I've got velocity as a function of time. That's all I mean by inverting this equation. So I've got t as a function of velocity. Maybe it'd be more efficient for us to have velocity as a function of time. Just switch them around.
and we want to know what the capsule diagram would look like. And let's say we're
So this is the trick we're going to do to go from
5%.
acceleration to
So drawing the
velocity.
in this case,
What if we need to make that next jump to position?
we're asked to calculate something related to this problem.
So one method I kind of already outlined.
First step, you figure
Method 1, we'll call it
out what is happening. Because if you just read that
invert
kind of
t of v, time as a function of velocity,
may not be,
to
but
velocity
the word problem
as a function of time. And then this is just
So let's look at our cash flow.
time rate of change of position. Integrate that with respect to time, just like we did for the first problem. So
We have to deposit right now.
method 1, a little bit of algebra,
We'll draw some
and then get us here.
to indicate that we're going to have to make some deposit right now to make this thing possible.
Method 2,
And sometimes usually
chain rule.
that arrow is bigger.
We'll get a little sneakier.
T equals question mark. I don't know. But what we do know is the outcome that we want, which is that
These are all these math words that you've heard of before that
1 year after
you don't use all that often. So
we want to be able to withdraw $2,000 per
chain rule.
year
This is our method 2.
for 5 years, and then $3,000 per year
I have
following
acceleration as a function of velocity.
an entire study period or time period of
dv dt. I want,
we're told that
I'm going to say chain rule to get position.
of 8.5%, which we write underneath the diagram.
I want to get position. In order to get position, I'm going to introduce
The reverse
my position variable,
is that you could be given just this cash flow
ds over ds.
and asked to solve for
So, haven't done anything wrong.
So here's what,
Something divided by itself is 1. I've just introduced a very fancy 1.
so even if you're like, well,
I'm going to rearrange these guys a little bit.
ever, I don't really care. It's okay.
dv ds,
I get it. But
ds
at least be able to make sure
dt.
that you can interpret them.
The old switcheroo.
And we'll look at them a lot with numerical.
And I do that because ds dt
We'll have more than just this one time to look at it and figure out what
is just velocity.
so don't be worried. But
So now,
as we continue to go through
creeping closer to something, I've got acceleration as a function of velocity is equal to velocity dv
so this is a concept we'll kind of come back
ds. Separate variables.
So let's
Get my v's on one side and my s's on the other.
economic equivalent.
ds is equal to v dv over
Equivalent is another thing we'll do a lot.
acceleration as a function of velocity.
Interest rate, the time value of money.
Now we can
Try to
integrate.
determine different amounts of money at different points in time. That we
Look
can
at your variable,
consider to be economic.
ds. I'm integrating the left-hand side with respect to s.
So we might use information
Right-hand side,
interest rate and
velocity.
time, and think about where those different payments or cash flows might happen, and how you might make two amounts of money at different points in time.
Honestly, I can tell you my brain would never think to do this. You know,
So,
I would get to
for example,
method 1.
we have different sums
I'd
of
get to
money
t as a function of v,
periods. They could be equal.
integrate that to get velocity as a function of time, and then go again. But that's me. That's how my brain works. I would think that
equivalent to 100
this integral
years from now if
may be a little sneaky sometimes,
of 6% per year
right?
or a rate of
And my calculus skills, I don't know if I'd have that in my bag of tricks without
are different
Maple or
when they're happening at different times.
calculator help.
They're economically equivalent
Okay,
in this scenario. So it's kind of a concept that we'll talk about.
2 down, 1 to go. We've done acceleration as a function of time. We've done acceleration as a function of velocity. That leaves us
So we're going to finish this on Thursday. Yep, Thursday.
excel, or let's do this. Acceleration as a function of position.
I'm going to hang out here for a couple minutes and go up to my office.
And this one
Want to pop into
Commonly, springs are the culprit.
After this, before 3:49 if you have it. Otherwise, you can email me questions.
Chapter or two down the road when we start talking about forces from springs, the chance of you remembering what we talked about on day 2 of class, not good, so I'll try to kick in a reminder when we get there. That's how you can solve these. So, acceleration as a function of position. Always starting in the same place. Acceleration is the time derivative of velocity. Here, just like we just did with the chain rule, we got to introduce a position variable. So we bring in that fancy one again, ds over ds. Same trick we did before. Now we'll just do it without rewriting. ds over dt, that's velocity. My other ds, I'm going to pair up, separation of variables. I'm going to move it over to join its buddy, acceleration. So what we get here, acceleration of s ds is equal to v dv. S is on one side, position, velocity is on the other. Integrate s0 to s, integrate v0 to v. We don't know what that acceleration function actually is, so not a whole lot we can do there. But we can fix up the right-hand side. So if I integrate v with respect to dv, v squared over 2, evaluated at v and v0. Left-hand side stays the same. So its right-hand side becomes v squared over 2 minus v0 squared over 2. Pretty this up, solve it for v. V squared is equal to v0 squared plus the half gets brought over and makes that a 2. 2 times the integral s0 to s, acceleration as a function of position. These are all equations that you're not going to memorize. All you're going to have to memorize as we work through this is, I need a position variable. I don't have a position variable in here. I better use chain rule to bring it in. Oh, now I got this. V is on one side, S is on the other. Use separation of variables. You get here. Like, none of this is things that you really have to remember. I guess the gotchas you got to remember is acceleration is dv dt. Remember that. Remember the process to get from one to the other. You're going to be just fine. All right. So what do I have here? I want to get to position now. I got velocity as a function of position. And remember that velocity is ds dt. So separate variables. Get the t's on one side, the s's on the other. dt is equal to ds over velocity as a function of s. Integrate. You're there. Right? That gives us this bottom box. So, how to manipulate these equations when you only have position, you only have velocity, you only have time. What do we do to move back and forth to get us here? So I said this is the only one you needed to know, but probably need to know this too. Velocity is the time derivative of position. You got those two things down. you're comfortable with a little bit of calculus, a little bit of algebra, you can get where you need to be. All right. What if acceleration is constant? Let me just jump back a slide here, or a box. Hey, this expression for velocity as a function of position gets pretty easy if acceleration is just due to gravity. Maybe that's g. Or maybe it's 7. Or maybe it's 3. It's a constant value. Then I'm just integrating ds with respect to s0 and s. I'm going to get a nice little equation to fall out of that. And that's kind of along the lines of what we're showing here for constant accelerations. If you are lucky enough to have your acceleration be a constant value, a bunch of these integrals that we just worked through are super easy because you're integrating a constant. And what falls out of them is this little pack of equations. So that one that we just did at the bottom, that's your, this one. This one just fell out of acceleration as a function of position, right? It doesn't matter. Your acceleration is constant, so it's not a function of anything. It's not a function of time, not a function of velocity, not a function of position. It's just constant. We'll use these guys for projectile motion. Pew! The only thing that we're worried about with projectile motion in 202, or this class, is gravity. Gravity's constant on Earth pointing down. So we can simplify these. If we were getting fancier and it was projectiles, maybe we're also factoring in drag. Acceleration is a function of velocity and time. Okay, now it's harder. We'll leave that for advanced stuff. So we'll look at these acceleration constant pieces next time we get together and we do projectile motion. The gotcha is that this box is really big and these equations are really easy to apply and they are really incorrect if your acceleration is not constant. So don't fall in love with these because they're easy. Remember that they're only to be used in the case of constant acceleration. And when you use these on your exam, like some of you will be penalized. Okay, helpful information. I already primed you on this. You don't need to know all that stuff. You just need to know acceleration is a time derivative of velocity. Understand how to use chain rule to bring in the variables you need. Understand separation of variables to move things so that you can then integrate. All right, what do we got? Example problem. Objects falling in water. Fluids problem. So what we have in the problem statement, acceleration is given as g minus cd, drag coefficient, doesn't matter to you, divided by the mass times the velocity. Here is our expression for acceleration. If you're given all this stuff, g, cd, mass, and I want you to get to velocity, can we use this? What do you think? Yeah, exactly. So can we use this expression? No, because what do I have? In this problem, we're given acceleration as a function of velocity. This is my acceleration term. It's a function of velocity. I cannot integrate it with respect to time. We need to use one of our other tricks. Hey, I told you, when you see fluids problems, there's going to be acceleration as a function of position. We want velocity. So how do we get there? A is equal to dv dt. I want velocity. I've got acceleration with velocity. I got to get these guys on the same side. Move the dt to one side, dv over a of v. So this is our problem. This is how we're going to solve it. And this is, I think, exactly a homework problem, so you might as well follow along. So if we integrate dt, we integrate dv over acceleration as a function of velocity. My time side, t0 to t. My velocity side, v0 to v. I'm hoping we can get this side. Left-hand side, t minus t0. Right-hand side, sneakier, v0 to v, dv over my acceleration term. That's this guy. G minus cd over m times v. Oh, man. High school again? How do I integrate this beast? U substitution. Let's kind of make this look like something we know how to integrate. du over u. So if I use a u substitution to make this thing look familiar so I can integrate it. Make the denominator u, g minus cd over mv, and then du, taking the derivative of this guy. G is a constant, that goes away, minus cd over m dv. For my u substitution, I want to swap out the v's and get it in terms of u. So this denominator is u. This numerator, dv. I want to solve this guy. So I've got that minus m over cd du is equal to dv. So now I can substitute in for dv. I can substitute in for this denominator. And my numerator becomes minus m over cd du over u. This is a constant. Boop. Pull it to the outside. Our limits of integration were v's. Now we got to rewrite these in for u. So my u0, hey, I've got a u over here. So just substitute in for whatever v0 was. G minus cd over m v0. U, same thing. G minus cd over m v. Integrate du over u. I jumped back a few slides and told you that this was ln of u. Problem solved. So this takes you 90% of the way through your homework problem. The other 10%, I'm leaving for you guys. All right, 1 minute left. I want to throw in one more thing. Here's an example I'm not going to do. By the way, this example was constant acceleration, which I think is pretty easy. The one thing I want to talk about real quick is the angular part. So if I've got circular motion, and I've got theta as my variable. The linear case, we've got s, v, and acceleration. For the circular case, I've got theta dot, which is omega, and theta double dot, which is alpha. But all the problems are done the exact same way. All we're doing is swapping the names of things. So you can still be given acceleration as a function of position, but your position is now theta. You can be given acceleration as a function of velocity, but your velocity is now omega, and also time. So that's really no different. It just has some different names. So when you read in the book, take a look at that.